Hello and welcome to the Intermolecular Force Notes, London Dispersion Forces, also abbreviated as LDFs. And these are also known as induced dipole forces. You also will sometimes see them as van der Waal in some older textbooks. All of them mean the same thing. And this is the weakest generally of the 6 intermolecular forces. And we're going to see why it's the weakest in just a second. So I have here an illustration, if we remember, of CO2. Now, CO2 does have bonds with dipole moments that are, I think, they should be about 1. And so they are polar bonds, but because they are linear, the bond dipoles cancel out, so you have an overall nonpolar molecule. So if this is nonpolar, this then cannot have dipole-dipole interactions. And so we know, though, that CO2 can be a solid because that's how you get dry ice. Well, what then is holding one CO2 molecule to another CO2 molecule? Remember, anytime you have a liquid or a solid, you have millions of molecules being held together. So this is where we get into London dispersion forces. London dispersion forces are technically present in all things. They're just the strongest, or not really the strongest, but they're the most prevalent when we use explanations for things that don't have other intermolecular forces. So for example, the atoms in diamond experience London dispersion forces, but network covalent is so much stronger that the London dispersion isn't a factor. But there are some cases where London dispersion forces can explain things with molecules that have, that also have hydrogen bonding or also have dipole-dipoles. Okay, so coming back to this, what is a London dispersion force? So basically what happens in our CO2 molecule, for example, is even though we consider this to be nonpolar and the dipoles cancel out, if there's this pull, every once in a while, there's a little bit more pull on the right-hand side than there is the left-hand side. And that little tiny bit of pull for that very one fleeting second creates just a little bit of a negative charge. It's like a partial negative of a partial negative. It's incredibly, incredibly weak. And this can have an effect on the CO2 that happens to be next to it. And so this will make the CO2 molecule that's next to it, I'm just going to kind of draw it as a blob, it'll make this side of it positive, because if this is negative and they bump into each other, that will create a little bit of a momentary positive charge. And that will create a negative charge over here. Well, what's going to happen then? Okay, well, this molecule then is going to get a little bit positive and a little bit negative. Now, by the time these have formed over here and over here, this has actually erased, make this a little bigger. This has actually erased this dipole. So this dipole is now gone. Erase this. Because remember, it's not a permanent dipole. It only exists for a temporary amount of time. And though it's gone over in this original molecule, it's now caught on here and here. And then as it comes on down over here, it'll keep doing this to the other molecules as it bumps in. And it says it's doing this. What's happening to these other ones? Well, they're losing their dipoles, right? Because they only last for a minute. But if you get enough of the molecules to do this, and you get enough of them to create this temporary dipole, then this will catch on through the entire material and it will give a little bit of hold. Now, when it occurs, we call this polarizable, things that are capable of creating these induced or momentary dipoles. And certain things have a greater opportunity for those momentary dipoles. And I have a list of them later on, but they're things that are going to be larger molecules. So the more massive the molecule is and the greater the number of atoms, the more polarizable, the stronger the London dispersion forces are. And then also the if it's singular atoms, the larger the atom with more shells, the more polarizable it will also be. Okay, so we're going to take a look at our next example. So we take a next example. I have helium and argon, and obviously these are going to have very weak intermolecular forces because we see these as gases primarily, and it's actually very hard to liquefy either one of them. But if you were going to liquefy them, they would need to experience an intermolecular force, and since they don't contain, they're obviously not polar since they're singular atoms. And they're not metals, so they don't have metallic, and they're not ionic, and they don't have network covalent. So the only thing these would have would be London dispersion forces. And so we take a look at it. This over here on the right-hand side, okay, is going to be a lot more polarizable. Because if it has a larger number of electron clouds, you are going to have more probability that at some point, one of the electrons is going to end up just a little bit more to this side. And when it does that, that's going to create a little tiny bit of a negative, right? A momentary, again, it's not staying like this. It'll create a little bit of a negative side of the molecule. And over here, it will create a little bit of a positive because it has a little bit less time with those electrons in the shell. And when it bumps into the next argon, it will create this as well. Now, obviously, this is going to be a very temporary one if it's just a singular atom. And so this is going to be a very, very weak intermolecular force, which again is why we're going to see these as gases, noble gases, as gases, and not as solids or liquids at room temperature. So, and a couple important notes here. Everything has London dispersion forces. Absolutely everything experiences them to some degree. So if something is metallic, it also has London dispersion forces. So if something's ionic, it technically has London dispersion forces. It's just that they're so much stronger IMFs that we don't traditionally focus on the London dispersion forces within them. We focus more on the stronger IMFs present. The things, though, that will only have London dispersion forces, so these have no other IMF, London dispersion forces are going to be really important to discuss with them. So that would be nonpolar covalent molecules. So if it's not polar, it can't have dipoles, right? Diatomic elements, they're obviously nonpolar because the dipoles, they have no dipole. They have an electronegativity difference of 0. And then obviously noble gases. And of course, obviously, if they're going to have an IMF, this would have to be not when they're gases, but when they're liquefied. And with those, it's going to be an extremely small London dispersion force. So the boiling point is going to be extremely, extremely low. You're really going to have to slow the atoms down in order to get them to liquefy because that force is so weak. So what makes the London dispersion forces stronger are going to be with increased mass. Okay, so your larger atoms. So generally things that are larger will have stronger London dispersion forces. So if they're larger molecules. If they have increased atomic radii, if they're singular atoms, or things like the diatomics, the larger the radii, the stronger the London dispersion forces. And if we remember, if you have stronger London dispersion forces, which is a type of IMF, then you'll have higher boiling points, higher melting points. When we get into things like viscosity, surface tension, they'll also play a role. And the reason why both of these things will increase the London dispersion forces is because it creates more probability that you'll create a temporary dipole. We call that polarizable. And so you're increasing the probability that you're going to create one of those momentary dipoles that'll sort of start a chain reaction. I always like to think of it like playing tag, right? So like one person's it, they tag the next person, then that person goes and tags the next person. So even though everyone may be a turn being it, right? So being polarized for a moment, it's never lasting long. It's fleeting. It's moving from one to the next, to the next, to the next. But if you can get enough of these games of tags going, you can hold the material together in liquid or solid form. So let's take a look of an application with polymers. So poly means many and mer means molecules. So it's many of the same repeating unit connected together as one long giant chain. And when we say one long giant chain, this can be thousands to tens of thousands of atoms long in this chain. Most of them are going to be organic molecules. And so if we look down here, here's an example of polyethylenes. We see here that there's a really long chain, and I only put part of the chain of carbons, and then attached to these, where the dashes are, these would be hydrogens. Okay, so these would all be here where I'm highlighting right now. These would all be hydrogens. And so since this is CH, we know that this would be nonpolar, because even though these are hydrogens, they're definitely not hydrogen bonding hydrogens. And these don't create dipoles because CH is a nonpolar bond. So the only thing that's present in this polymer is London dispersion forces, because it's a nonpolar chain. What's really interesting is this is the type of plastic that makes up your plastic sandwich bags and some of your water bottles. So if we think about that, that's a solid at room temperature. Well, how could it possibly be a solid at room temperature if it's only London dispersion forces? So let's remember what we just talked about. How can we make London dispersion forces strong? If a molecule is really big, if it has a large mass, that makes it more polarizable. And in this case, it's going to be very polarizable because it's, and I've only drawn part of the molecule here, it's thousands of atoms chain long. And so that's going to create a very large molecule. And those large molecules, you kind of think of them like spaghetti strings. They become intertwined with each other. And you're really going to have a great chance for it to be polarizable because the molecules and the bonds are always shifting. And that's going to create a lot of probability for you to create one of these induced dipoles. Polymers, by the way, can include everything ranging from your DNA to all sorts and types of plastics, cellulose, which is in plants, and starch. So these are all different molecules that are examples of polymers. We find them everywhere. And we're actually going to do an entire lab related to polymers. Polymers will change their properties and the intermolecular forces they experience based on what unit's being repeated. So it's not always just a CH that's being repeated. You can repeat something like C double bond O. You can repeat all sorts of different types of organic functional groups. And as you change those functional groups, you'll change the properties. But no matter what it is, polymers will always experience large London dispersion forces because they will always be long chain molecules, which means they have a lot of mass, highly polarizable, and they're capable of creating those induced dipoles. All right, so the last two examples here is actually going to take us, loop us back to network covalent. So this first example right here is going to be for diamond. And we remember that diamond is network covalent, the absolute strongest of all of the IMF, network covalent. And so each one of these carbons up here is steric number 4, which means that they're all tetrahedral. Okay, so they have basically 4. We can also call this sp3 hybridized, just to review a little bit terminology. And so these are not flat. And as we looked at the 3D diamond structure in class, we could see that it was a chain going in all directions of these interlocking intramolecular bonds. And each one of the carbons is 109 degrees away from each other because of the tetrahedral geometry. If we come over to this structure, we see that we also have carbon bonded, but if we look at any of these steric centers, what's different about these is because of the double bond, they're steric number 3, which means that they're not tetrahedral, they're trigonal planar, meaning that they are, planar is really important because that means that they are flat. And this would also be sp2 hybridized. And so there's two really important parts about this. This is, by the way, graphite, which is kind of the cousin of diamond. Within this two-dimensional sheet, this flat sheet, you also have network covalent. But the network covalent is only for the two-dimensional structure. So you have these flat sheets, and within these flat sheets, these super strong bonds are holding them together. This changes, though, when we look at the 3D structure. So with diamond, its 3D structure, let's see if I can get that yellow. No. The 3D structure is going to be the same as the structure we just spoke about. Okay, so in every direction, it's sp3 hybridized, tetrahedral, and that's what makes up its entire 3D structure. Everything within it is network covalent. With the graphite, though, we have a big change. Each one of the sheets is network covalent. So we have a sheet here, a sheet here, I've highlighted them in green. But what holds one sheet to another sheet is not network covalent, but instead the weaker London dispersion forces. So each one of the sheets is held together by London dispersion forces, which is quite a weak force. And so when you write with your pencil, you're writing with graphite. What you basically are doing is you're laying one of the sheets is moving on top of another one of the sheets, and you're laying sheet after sheet across the paper. So what are you breaking when you're laying down the pencil onto the paper? You're breaking the London dispersion forces. You're not capable of breaking those stronger network covalent bonds that are within each one of the sheets. The other property that's really important about graphite, if we come back over here to the two-dimensional structure, is and this is not true for other resonance structures. It's just special for graphite. Because graphite will contain resonance, because you have pi bonds over here, the pi bonds are able to move. And they can not only move within one of the rings, they can actually move between the rings. And this is very important because anytime you are able to move electrons within a structure, so not just within the molecule, but within the larger structure, this will allow for electrical conductivity. And graphite is an excellent electrical conductor, which we wouldn't expect because it's just made out of carbon and non-metal. So this is a unique example where these carbons, which are sp2 hybridized and have resonance structures because of the pi bonds, they are able to allow the electrons to move within the entire sheet, and they're able to conduct electricity. And we'll do some experiments with this as we start to talk about the properties.